Hello and welcome back to Paleocast. My name is Dave Marshall, and this is the first in a special series of podcasts relating to a field trip that I've been invited on by Dr. Martin Brazeau of Imperial College London. I'm being flown out as the Palaeozoic arthropod expert of the team, and I'll be there to deal with all of the eurypterids and phyllocaridids we come across, along as documenting the whole process for outreach and hopefully your enjoyment. In all, this trip will last around 6 weeks, during which time I'll have no internet, electricity, running water, or even any toilets. It's going to be a gruelling trip, but hopefully one that will give you an insight into what life is like in the field. You will join us as we discuss the science, prepare for the trip, arrive in the field, go out digging, and finally wrap things up. You'll experience all the highs of discovering new and exciting fossils, and all of the lows of when we've just had enough. This expedition is a unique opportunity to share with you a single research project from start to finish, rather than just the results. In this first episode, we contextualise why we're going into the field. What is the current lay of the research landscape? What do we already know? And what are we aiming to find out about the early evolution of the jawed vertebrates, a group to which we ourselves belong? By the time you hear this episode, I'll already be well on my way to Canada, which I'm equal parts nervous and excited about, but this means that I won't be producing any more Paleocast episodes until September, so don't expect a full schedule of interviews in the meantime. But we already have a few recorded, so don't despair. Please give this episode a like and a share on social media, as it will really help us reach new audiences, and any donations to our PayPal account would be greatly appreciated. I've got a month and a half to break something in the field, so it'll almost certainly happen, and we don't get any funding from anyone but yourselves, so thanks to all those who have donated so far, and especially those of you who continue to donate monthly. We couldn't do this without you. We hope you enjoy this series. Hi Martin, thanks so much for joining us.
Yeah, thanks for inviting me. It's a pleasure to be here.
So, as with everyone that we have on the show, we like to get to know you first of all. So can you tell us all how you became a paleontologist?
I'm afraid it's not a very interesting story because I think it's the same story for probably at least half or so of people studying paleontology today, and that's you grew up interested in fossils, in natural history. Anatomy especially was always very interesting to me. I was maybe a bit of a roadkill botherer when I was a kid. And it's just a good thing that I turned out to be a biologist, because there's another career path that roadkill botherers end up on, but we won't mention that. So.
So was that like you'd be out on your bike with your brothers or whatever, and you'd just be poking things with a stick? Or was it
as
exactly. Extreme as you'd tell your parents to stop the car?
No, it'd be more like the first scenario, literally out on the road with my friends or my brother, and you come across a dead animal, and you're like, oh look, there's the heart, when you're young and you've hardly been to school at all up to that point, and you're wondering about these things, like, oh, you feel the heart beating inside of you, and you're like, what is that thing? What does that look like? Well, obviously you can't very easily go inside and look, but when you could see it either in illustrations and encyclopedias, so we had these celluloid sheets inside of an encyclopedia set we had as a kid that had all the layers of the human body. I was absolutely fascinated with that. And the same thing, you'd see it in another animal, and you could identify the same things. And I just found that really fascinating. I always was really fascinated by animal form, by shapes, by anatomy, how the body works. And so I was always naturally really attracted to that. And I think growing up, dinosaurs were really very much a big part of that, because you're looking at their skeletons, you're looking at that you have these big chunks of their anatomy that are understandable in a way in terms of other living things.
And what was your plan B when you were little then? What were you going to be if you weren't a paleontologist?
I think I probably would have gone into making cartoons and animation. In those days, I mean, I feel like it makes me sound like I'm much older than I am, but it was actually, in the 1980s and early 90s, there wasn't much in the way of computer animation. Everything was still hand drawn, and that was also really fascinating to me. So I think I probably would have gone into something like that and then gone extinct.
What was your favorite cartoon?
I don't know. I would say definitely the Warner Brothers cartoons, like Bugs Bunny and those Merry Melodies cartoons. They were absolutely ridiculous.
How did you end up studying fish then? So you're looking at roadkill, that's mammals, you love dinosaurs, that's reptiles. I mean, I guess they're all fish.
Yeah. Well, to step away from the world of vertebrates, the first fossil I ever found was a fragment of brachiopod that was probably only a couple of millimeters long. And it was in a piece of gravel that was underneath the back porch of my parents' house. And neither fish nor vertebrate really, but that moment, everybody has their finding their first fossil moment. And I can't imagine a more inconspicuous and boring fossil than that. But at the same time, everyone has that story of the first fossil and how it just ignites that fascination for you. And just that humble little fragment of brachiopod really just did it for me. That's all it took. The moment of realizing, like, holy crap, that's an actual fossil, was just kind of illuminating. And when somebody told me what it was, that it was this ancient Ordovician brachiopod, it opened up a whole new world of prehistoric life for me that I hadn't really appreciated before. So I'd appreciated things like dinosaurs, but everything else that's out there, you start learning about trilobites and brachiopods and crinoids and the things that were right under my feet growing up in an area that had no dinosaurs. And so very quickly, the whole world of paleontology became very interesting to me. And vertebrates were, of course, interesting, and dinosaurs were, of course, interesting. But I think I was always kind of, open to pretty much anything. It was as an undergrad that I worked as a project student, of course, in the Redpath Museum at McGill University. And the professor there at the time was Bob Carroll, of course, and he had a really great vertebrate paleontology undergraduate course, and the syllabus quite infamously promised everything from the origin of vertebrates up to the origin of mankind. And you were lucky if by the end of the semester you had made it up to reptiles. So most of my undergraduate training in vertebrate paleontology was fish. And I guess I just kind of got stuck at that level of the great chain of being. So.
Right. Well, today we're going to be talking about gnathostomes, which are a group of fish. Can you define what a gnathostome is?
More broadly, most vertebrates alive today are some kind of gnathostome, and those are the vertebrates with jaws and teeth, but also paired fins or paired limbs, and have mineralized skeletal tissues, so bones, calcified cartilage, tooth enamel. These structures identify gnathostomes, or jawed vertebrates. And all of these animals, of course, are united by a single common ancestor, which we think had all of these features, or at least very nearly most of these features.
And what kind of thing would it have evolved from?
Gnathostomes would have evolved from some sort of jawless vertebrate, a jawless fish, of course. And these, we find fossils of these, of course, but we have living representatives. But we find fossils of these as well, and we see that some of them have some, but not all, of the identifying features of the jawed vertebrates. But we can find within the fossil and living record at least a number of fishes that lack jaws, lack paired fins, and lack mineralized skeletal tissues.
Okay, and do we find any of those jawless fishes alive today?
Yeah, we do. The modern hagfish and lamprey are living examples of jawless fishes, of course. And they're alive today, but they're quite a bit less numerous than modern jawed vertebrates.
I mean, very less numerous.
Yeah.
Very less numerous. That sounds like a horrific sentence. Anyway, that's the academic level to which we're working today. So
that's perfectly fine.
Yeah, in the past, were there a lot more of them? I am assuming then, yeah.
Yeah, absolutely. So if we go back to the Silurian period or the Ordovician period, the vertebrate fossils that we find are predominantly jawless fish. These armored jawless fish we call ostracoderms, but it's a bit of it's a paraphyletic group, of course, so it's one of these non-existent arbitrary assemblages of things that are just defined by things that they lack, of course, which is that they're not jawed vertebrates. But they're a diverse set of things that had all kinds of body forms, different levels of armor and scale covering, and presumably had very different ecologies as well.
So when the jaw evolved then, what did it bring? What did it do for those newly established jawed vertebrates?
Right. So that's something we're kind of trying to figure out. And there's a bunch of different ways this question is being tackled. But for a long time, we've thought about the jaw as one of these great leaps in invertebrate evolution. When we think about things like the origin of flight or the origin of terrestriality, tetrapods crawling onto land, the origin of jaws is one of these classic textbook pictures of an evolutionary transition. And what it brought, of course, was a shift from feeding on small detritus or particles, suspended in the water column. So a shift away from feeding on that sort of stuff to actively predating, actively attacking prey and eating it. So it brought about the ability to really consume other animals, as it were, larger other animals.
And is that simply because they can catch things with its jaw, or is it that it can chew?
They almost certainly weren't able to chew. Eventually, it did bring about the ability to crush shells. That was probably one of the first major mechanical inventions after the origin of jaws. But probably only the ability to catch prey that was big enough to be swallowed. Small enough to be swallowed, rather.
And if I think of a fish and its jaw moving, the first thing I think of is my goldfish that I used to have. It was called Superman. Rest in peace. And he would just have his mouth going the whole time. Is that a part of it? Does it assist in the breathing?
So just after I finished saying what I just said, I of course realized that I'd forgotten to mention that a big part of the origin of jaws is probably the introduction of a very elaborate valve in the head for breathing. It brought about the ability to basically pump water through the mouth and over the gills. Now it's thought that to some extent, of course, some jawless fish can do this, but certainly the volume of water that can be moved through a mouth that's sort of closed off by jaws is considerably greater. So it's thought that there's one hypothesis that the origin of jaws really had to do first with the origin of gill ventilation.
The evolution of the jaw is perhaps intrinsically linked to the gills, because I'm sure that I've read somewhere that it actually evolved from a pair of gill arches. Is that true?
Yeah, so that's one of these classic textbook pictures. I often show it in talks or in lectures to undergraduates. That if we look at the textbook picture of the origin of jaws, we have a picture of three animals. Usually, one of them is a jawless fish of some kind with a series of gill arches all the way around the mouth. And no jaws. And at the other end of the spectrum is a sort of fully formed shark-like head with jaws and another arch behind it that's sort of suspending the jaws to the head. And that latter animal, that's a real thing. That's based off of modern sharks, for instance, and some sharks that we observe in the fossil record. But then there's this intermediate picture, which is the animal that has the gill arches somewhat modified into kind of a precursor of jaws. And the first two images in that overall image are organisms that do not exist. They've never been observed in nature. We've never observed anything like that at all. It's completely hypothetical. The closest thing we could get to it is something like some of the Burgess Shale animals, like the recently the recent paper on Metaspergina from the Burgess Shale from the Cambrian about 540 million years ago, was this animal that had a series of segmented gill arches in the head. But the intermediate animal certainly doesn't exist. And if we look at modern jawless fish, and to the extent that we can get this information from fossil jawless fish, their mouths are already quite specialized. They don't have jaws, as far as we can tell, or nothing quite like modern jaws, but they're specialized into some other structure, either a ring-like structure, as you see in lamprey, for instance. It does not look like a jaw in any way. So it's really, we see that picture, but there's really not a lot of real data supporting it, apart from the fact that it is an appealing and convenient scenario.
Are there any other hypotheses about how the jaw evolved then?
Well, to some extent, there's a certain amount of truth to that hypothesis. So a lot of it is based on the embryology of the head. So the gills and the jaws and the intermediate arch, called the hyoid arch, which in ourselves forms part of the inner ear, or middle ear, and in fishes forms a jaw suspension system. So those arches, the jaws, the hyoid arch, the gill arches, all form part of an embryological series of structures that are related to each other in terms of how they develop. So there is some relationship between the jaws and the gill arches, but since then, and this is more the province of comparative molecular biology, which is not something that I do in my own research, but that work is always exploring what sort of genetic changes have to take place in order to shift from a jawless state to a jawed state. And so some of the changes in that idea are really at the level of the expression of various developmental genes. But as far as a whole new scenario of how jaws have evolved, nothing that's quite captured the imagination as that classic textbook picture.
Well, regardless of whatever method it got there, we do now have jaws. So when in the fossil record do we see the first gnathostomes?
The earliest gnathostomes, it depends on whether or not you're referring to ones that we're reasonably sure are gnathostomes or are things that we think might be gnathostomes. So the earliest fossils that we've attributed to gnathostomes are either in the late Ordovician or earliest part of the Silurian period, and these are really just isolated scales, denticle-like scales attributed to an animal like an acanthodian, a spiny shark-like animal. And then it's only really much later, once we get into sort of the middle to late Silurian period, that we actually start to find skeletal remains that we can be confident are the remains of jawed vertebrates. And again, a lot of this is fragmentary stuff, but we're reasonably confident to what those what animals those fragments can be attributed to. We know what the rest of the animal looks like based on a later representative, for instance. But really getting into the late Silurian, that's when we start to find the oldest body fossils. And in the late Silurian, they're extremely rare. But we find evidence of spiny shark-like fishes. And more recently, especially coming from China, we find representatives of the placoderms, or placoderm-like fishes, which are the armored jawed fishes, most famously Dunkleosteus from the late Devonian, so somewhat farther ahead in time, and then early bony fish as well. So right at the end of the late Silurian, the two major divisions of living jawed vertebrates are already showing up in the fossil record.
So when we see the first gnathostomes in the fossil records, the skeletal ones, the placoderms, you said, were they some of the most simple gnathostomes? Were they fairly derived when we first see them?
Yeah, so when we start seeing evidence of the first placoderms, what's really remarkable about these things is how much they resemble sort of the early representatives of bony fish. So the discoveries by Zhu Min and colleagues in the fossil fish deposits in Yunnan, they found animals like Entelognathus and Chilinyu, which have, unlike any other placoderms, at least recognized so far, they have this very elaborate bony face where the jaw skeleton, there's an extensive external bony jaw skeleton formed of different parts that we could recognize as a maxilla and a premaxilla and a dentary bone, and all these units of the jaw, as it were, that we recognize in modern bony vertebrates that we have all the way up into even humans and other living tetrapod groups. So that's really remarkable that we're seeing these animals showing up quite early and showing that those traits of skeletal or those skeletal jaw traits of bony vertebrates actually have a much more ancient heritage. And this really kind of upset the apple cart in terms of how we classically thought about the evolution of jawed vertebrates. For a long time, a very strong emphasis was placed on thinking about sharks and shark-like animals as being primitive. Their fossils are certainly the ones that show up earliest in the fossil record. But there's probably a very good reason for that, which I could explain a bit later. But while they show up in the fossil record, we don't consider their anatomy to be as primitive as we once thought that it was.
So if these spiny sharks are the first gnathostomes that we see in the fossil record, is it fair to consider modern sharks as being incredibly primitive?
Right. So when you turn on a BBC documentary or the Discovery Channel and Shark Week is on, and almost every documentary or every other documentary will will reaffirm this notion that sharks are unchanged for 400 million years, that they're these, primordial fishes that really, just harken back to a very ancient time. And in some ways, that's true. And for a long time, we thought that, for instance, the lack of bone, especially on the outside of sharks, so the sharks are covered in these very, very fine tooth-like scales over the surface of the body, rather than a plate-like bony armor that we see in bony fishes and which is retained in many parts of our own anatomy. We've classically thought of that armored condition as a novel invention, and that the ancestor was very shark-like and didn't have an armor. But now that's just completely turned on its head. We now think that the opposite is actually true, that the covering of fine tooth-like denticles is actually a derived state, and that the common ancestor of living jawed vertebrates probably had an extensive bony armor and probably looked a lot like an early bony fish, or even a placoderm.
So once they'd evolved, how quickly did they diversify?
Yeah, so that's a really good question. So we think that jawed vertebrates appeared perhaps as early as the late Ordovician period, looking at something like 440 some million years ago. But they really don't take off in terms of their diversity until well into the Devonian period. And so they have something of about a 40 million year lag between their origin and their ultimate diversification. But when they do, their diversity really takes off in the middle Devonian period. And that's when we start to see really lots of representatives of placoderms, bony fishes, and a few sharks, and acanthodians.
So what had changed? Is it anything that we can point to in the later groups and say these all have this kind of characteristic that the earlier ones didn't, or is it just not that simple to put your finger on?
Yeah, it's really not that simple. And that's really the next question that we're trying to get at, is why is there this lag? It's not the only place where we see this. We see this in a lot of groups where the major anatomical novelty or novelties arises millions of years before it ever leads to any sort of explosive diversification. So it's a really, it feeds into a very general question about major evolutionary transitions. We see this with early tetrapods. We see this with the origin of hypsodont teeth and in mammals. We see this really in a lot of different places. And so, this is not the only one. So the question is, what constrained gnathostomes from diversifying early on, and what led to that eventual explosion? And the answer is we really don't know. We have a lot of ideas, like there may have been competition from other vertebrates, including jawless fishes. There may have been sort of too much fragmentation of the continents at that time, so that they were quite restricted. They were quite highly endemic in one part of the world, and then only later were able to spread as sort of continents came together, and they were not separated by these vast, untraversable expanses of ocean. And it may also have to do with the innovation of particular anatomical traits. So we look at the animals that really diversify earliest or sort of show up earliest in the fossil record are animals like acanthodians and shark-like fishes. And these animals, which we now understand to have lost their armor, their ancestral armor, may be adapted to being much lighter. So they've shed their armor, they're much lighter, so they're much better at dispersal, at escaping competitors and predators, and that's why we see them earliest in the record, and that's why we see them with the most global distribution early on in the record. But we really, really don't know for sure. So we really have to sort of get at this using databases and quantitative methods to actually understand and test these problems.
How good is the record of gnathostomes from the early Ordovician to the Devonian? Could it simply be a sampling thing? The diversity was always there, but we just don't find the right rocks, or we don't find the fossils in high enough numbers?
I imagine it's a little of both. So the places we're starting to find the earliest placoderms and earliest bony fishes are, of course, places like South China and Vietnam, and some very peculiar, quote unquote, primitive early gnathostomes, as it were, are found in Australia, for instance. And all of these continents were actually quite close together in the Silurian and Devonian. They're in what we call East Gondwana, or sort of that related area. And so it could be that, and we think increasingly that this may be where those groups really first diversified, but they were isolated from the rest of the world until later. And so our record, which we've primarily built up from North America and Europe, really lacked those animals because they simply didn't live there. We were sampling in the wrong places, as it were. So having just said that most of the early, sort of the early bony fishes, early placoderms, which are really kind of these game-changing fossils, are being found in China and Australia. There's a few tantalizing clues from Europe and North America, from the late Silurian, and parts of Russia. And so they really give us a hint that we're not getting the full picture based on how and where we sampled the Silurian strata in North America and Europe and Russia. So these are animals called Lophosteus and Andreolepis, and they're really only known from isolated fragments. We don't have any articulated or dissociated skeletons of these fossils. They usually turn up in microvertebrate samples and in spot samples taken from fairly restricted exposures. So that means the bedrock isn't very well exposed compared to a lot of other places, like out in desert environments, of course. So they might be a coastline or a river exposure. And so we get these little glimpses of these animals, fragments, a scale here or a little jaw fragment there. But they're really pivotal. They've become really central in debates about how jaws and the facial skeleton evolved and how teeth evolved. And there's really a lot of dispute about these fossils. So what we'd really like to know is, of course, more about them, and also, if we could, have more complete skeletons of them.
So what do we still not know about gnathostome evolution?
Quite a lot, and it depends who you ask, because most people in the Society of Vertebrate Paleontology are working on some kind of gnathostome or gnathostome group. But there's a lot of outstanding questions regarding the earliest gnathostomes, and that's, at the most basic level, is how all these things are related to each other. Because obviously, if we work out how these things are related to each other, then we can actually really begin to detail how all their formidable traits like jaws and teeth and paired fins and everything evolved. But as much as we've made quite a bit of progress in figuring out how these things are related to each other at a very sort of broad scale, it almost opens up more questions. The more things we find, it's this classic problem of you discover one thing, or you answer one question, and 10 more open up. A big problem, for instance, is what are all the placoderms? We traditionally thought about them as kind of their own family, their own branch off the side of the gnathostome tree, kind of the sister group of modern gnathostomes, as having something to do with the origin of gnathostomes, but really a family in their own right, with their own sort of parallel history. And then during my PhD work, I suggested in a phylogenetic analysis that I published, which was really the first kind of broad-scale numerical analysis of this problem. I suggested that actually, no, they're not a family, that some of these things are more closely related to modern gnathostomes than others, and that some of these things look like jawless fish, and that's possibly not a coincidence, notwithstanding the fact that in many placoderms we've never actually observed their jaws. So I pointed this out and provided character matrix and analysis in support of it. And since that time, a lot of other research groups have built on that and have continued to find that same result. But, and this is kind of a big caveat, well, there's actually two really big problems, at least in my mind, with my own hypothesis, which is, one, as we add more data, the actual statistical support for the hypothesis gets poorer and poorer. So it actually gets a lot noisier. So while the analyses also agree that some gnathostomes are closer to jawed vertebrates than to others, they don't really agree on all the details. And then there was the discovery by John Long and Kate Trinistick and Per Ahlberg and colleagues working on the placoderms from Gogo and some from Scotland and elsewhere, which was the discovery that all the placoderms, regardless of where they fell on the tree, appear to have had internal fertilization and potentially live bearing of their young, which is a really sort of complex life history trait, and not something that appears and reverses very easily. Well, here's the snag. If we accept that phylogenetic tree that I proposed back in 2009 or so, then we actually have to accept that internal fertilization and possibly live bearing of young not only evolved in the ancestors of gnathostomes, but then switched back to external fertilization. So most modern fish, to give a bit of background here, which I should have given before, most modern fish don't have copulatory reproduction. That is, they don't engage in copulation. They don't have like an intromittent organ like a penis or a clasper or anything like that. They just have the female lays eggs in the water, and then the male just disperses sperm into the water and hopes for the best. Well, in a number of fish groups and vertebrate groups, we see the switch from external fertilization to internal fertilization. Sharks, quite notably, have internal fertilization. And now it turned out, of course, that placoderms also have it. But the thing is, we don't really very often see, I can't really think of any instances where we do have evidence that there's been a switch back to external fertilization. And so we're actually in a situation where if we accept that placoderms aren't a natural family, then we have to accept a kind of biologically dubious scenario about their reproductive biology.
Wow, I did not expect to hear that. So, where are we going to find the answers to all these questions that we have about gnathostomes?
There isn't going to be one place. The whole progress that we've been seeing with this field actually is the input coming from a lot of independent research groups in China, in Australia, in Sweden, in the UK, in the US, all these different groups working quasi-independently of each other, and really attacking this problem from different sides. A lot of the really cool stuff we've been finding, of course, has been coming from China and coming from Australia. But I think we can't forget the really fascinating areas in North America and Europe that we really haven't studied in detail. And actually, to take a step back, for a number of years, I've been working in, of all places, in Western Mongolia. And it's taken a while for all of that to kind of reach a sort of come to a head, as it were. But now we're really starting to find interesting results in that. So I'm looking forward to starting to submit the publications on that in the next couple of months. But where to next? Well, really need to look at the Silurian. We need to look at this older interval. We need to understand a lot of different variables, not just who the jawed vertebrates are, of course, but we really do need to find more jawed vertebrates from this much older interval, from the Silurian period, and ideally, if we could, more from the Ordovician period.
I think we should go.
I think we should.
Paleocast was brought to you by Dave Marshall, with Joe Keating, Laura Soul, Liz Martin-Silverstone and Caitlin Colery. It was made possible by funding from the Paleontological Society and the Paleontological Association, but the show now relies on contributions from you, the listeners. If you've liked this episode, please consider donating, and thanks to everyone that's helped out so far. We'd also like to thank the Ocean Collective for use of their music. Please visit paleocast.com for the supplementary material to this episode and for our archive of past programmes. Subscribe to our Twitter feed @Paleocast and like us at facebook.com/Paleocast to get all the latest news.